This is John Black, Super Chemist, Polarizer's Fundamentals, and the 3 Polarizer Paradox.
We actually made a second video showing more of the details for how this works, which you can find on 3 Blue 1 Brown, but right now, let's just go ahead and hit the main point. First, photons are waves.
And see, he admits, okay, he knows photons are waves. Meaning what? What does that mean? That means he knows that they oscillate. So if they oscillate, he knows that the probability percentages should also oscillate. Okay, he knows. He's not a 3-year-old. Okay, he knows.
Waves in a thing called the electromagnetic field, and polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening.
See, he just admitted he knows they rotate them. They can't just let the verticals come in, right? Look, if you have 180 degrees of freedom, meaning 180 configurations, right? Each degree has the same percentage of, photons in that plane, you know what I mean? So that means if only the vertical gate got in, only 1 out of 180 configurations came in. And they're saying that half of the light comes in. 180 does not equal 1/2, right? So obviously, they're taking the vertical ones and they're also taking the non-vertical ones. They're taking a percentage of every degree of freedom, okay? But obviously, the more you're closer to a 0-degree difference from the filter, the more percentage will get through, you know what I mean? But it takes a percentage of every degree of freedom, even at 89 degrees, it takes some of it, okay? Obviously, it has to rotate some of the light in order to get 1/2 instead of 1 out of over 180. See, 1 over 180 and 1 over 2, which is 50%, they're not the same thing, okay? So obviously, he knows it, right? He knows math. You're saying this guy doesn't know that 1 over 2 is not equal to 1 over 180. He doesn't know that? He knows, okay?
But unlike a water wave or a sound wave, photons are quantum objects.
You don't have to constantly smash in everyone's face this word quantum, okay? You're a Morty. That's what these people are. They Morty up the physics, okay? They've invested the planet like roaches. You don't have to. It's like anything that they disagree with, they call classical. Okay, their definition of classical is moronic. Okay, they'll be like saying, we know that there's atoms because quantum stuff is true, and classic physics says that there's earth, wind, and fire, and they don't believe in atoms at all. They'll go back 3 million years and say this is classic physics. No, you're a liar. Okay, so today, quantum physics means you believe in magic, and classic physics means you do not. That's the only difference. And yes, I do believe in quantum things. I just don't believe in the magic part. The magic part is stupid. Leprechauns do not exist.
Such, they either pass through the polarizer completely or not at all. And this is apparently probabilistic, like how we don't know whether or not Schrodinger's cat will be alive or dead until we look into the box.
For anyone uncomfortable with the non-determinism of quantum mechanics,
of course it's leprechauns.
It's tempting to imagine that a probabilistic event like this might have some deeper cause that we just don't know yet. That there's some hidden variable describing the photon's state that would...
Do you see this? Look at this! Look!
Deeper cause that we just don't know yet. That there's some...
Look! He literally is drawing the photon oscillating. Oscillating his E field, his B field. And he's thinking that what? The oscillations don't transfer over into the polarizer with his E field and his B field, and this oscillates just like the probabilities. Like, this is insane.
Hidden variable describing the photon's state that would tell us with certainty whether it should pass through a given filter or not. And maybe that...
Yeah, if you could see small enough down there to see it, and you could see the oscillation of the energy going back and forth, then yes, you could figure it out. Okay? but we can't do that. So these people are like retarded.
Variable is just too subtle for us to probe without deeper theories and better measuring devices.
Look at that,
Or maybe
look, and then he say, look at this, say we can't figure it out. Boy, we just got to go deeper into. And then he still has it right there. He has the answer right there that he just drew, and also it just
somehow fundamentally unknowable, but still there. The possibility of such a hidden variable seems beyond the scope of experiment. I mean, what measurements could possibly probe at a deeper explanation that might or might not exist?
Yeah, the oscillation of the B field wow.
And yet, we can do just that.
With sunglasses and polarization of light. Let's go ahead and lay down some numbers here. When light passes through a polarizing filter, or oriented vertically, and then comes to another polarizing filter, oriented that same way, experiments show that it's essentially guaranteed to make it through that second filter. But if that second filter was tilted 90 degrees from the first, then each photon has a 0% chance of passing through. And halfway between, at 45 degrees, there's a 50-50 chance.
What's more, these probabilities seem to only depend on the angle between the two filters in question, and not on anything that happened to the photon before.
Photon forgets this, the first filter. These people are like morons. No, you rotated. It only matters what the second filter was. It doesn't care what the first filter does, because it only matters how you rotated the freaking E field. This E field was rotated different than this one. And so when it goes, come on, man. Obviously doesn't care about that one. Why would he care about this? Photon forgets this. He doesn't forget. It's just that you rotated him. It's not like he's in this thing and then he just forgot. He said, oh, no. No, you purposely put a filter in between the two filters there and rotated the photons purposely and knowingly. And then you acted like a moron. and said, I don't understand what's going on here. I just rotated the light and it acts different. Why would it act different? I didn't do anything to it. All I did was rotate it. Well, this makes no sense.
Including potentially having passed through a different filter first.
But the real numerical weirdness here happens for filters oriented less than 45 degrees apart. For example, at 22.5 degrees, any photon which passes through that first filter has an 85% chance of passing through the second filter.
Yeah, that's literally how every antenna on the planet and the whole universe works. That's how antennas work. Why is it magic when your antenna is made out of polyvinyl polymer doped with iodide, or just wires, little wires? Why is it then, when it's plastic, your antenna, it's magic? But if your antenna is metal and it's made for radio wave light, then it's not magic. And it all makes perfect sense. Why is this?
To see where all these numbers come from, by the way, check out the second video.
What's strange about that last number is that you might expect it to be more like halfway between 50% and 100%, since 22.5 degrees is halfway between 0 and 45, but 85% is significantly higher. To see concretely how strange this is, let's look at a particular...
Look how, it's just so strange. He can't understand this. He's dumbfounded. He doesn't understand why when you have an object that oscillates its position, the probabilities would oscillate. It must be leprechauns. To use these, when you have 180 data points and you use 3 data points to show your point, you're a moron or you're a liar. Okay? Now, why do these things oscillate? I wrote down the probabilities, right? Percentage probabilities for all the 22.5 degrees is on the top here. I took all the 15 degrees. These are all 15 degrees apart, right? It's a sine wave. It oscillates. See how I got a lot of space in between here and here? That's because from here to here, you're just standing there. When you look at this, you're this photon E field, right? Here's the E field. You're not that line like these. We draw these lines. That isn't the E field. The E field is a energy particle or energy or whatever energy thing that oscillates back and forth. Okay, so here's the E field. Okay, and I drew it, like a line. But the B field would be at this point or this point or this point. Pick one of these blue points. He'd be at one of those points, right? He wouldn't be this whole line. Okay, he'd be here. He'd be here, here, because the same way with the E field. It oscillates. It isn't a line. It's a energy, whatever particle that oscillates, right? So when this oscillates, it has to be here because it stops. You figure when it's at the middle, right, it's going the fastest it can go. It decreases its, it deaccelerates, then it gets up to here, then it stops, literally stops. And then it accelerates a little bit, but it's still slow. It accelerates, and then it gets to here, it's the fastest it can be. Then it slows, decelerates, deaccelerates, then it stops. You can see, so if you stop here and you're slow here, you're going to have a lot more time here and here. Then here you'll have no time because you're going the fastest you can go. You're just zipping right by it, right? Obviously, you're going to have oscillating probabilities, okay? Look at the lines. See how there's a little space, this is the middle. There's a little space here, then a big space, then a bigger, then it accelerates. It's not just that they get bigger, they accelerate, okay? Same here. Here's the middle. You get a little bit more. This one, it's accelerating one way or the other, and it is oscillating, right? It's oscillating. So that means what? That means that if it's more probable that the E field is here, and there's more probable that the E field is here and not here. You know what I mean? Look at the sine wave. It's flat on top, right? From here to here, it's flat. Then now look at the hill. Then the next one, it's down here, it's straight up and down. Here, it's horizontal. You know what I mean? If I took this, right, because this is for position. Say I changed these 100% and 85% and all that. I changed it into millimeters, right? Showing where the position is of this E field from the photon, right? But you see how it accelerates. The position accelerates on where it's going to be, just like the probabilities accelerate. I could take this and plot it over here, like I said, and make these, instead of it be percentages, make it be millimeters. You know what I mean? I would plot the same exact graph with these same exact numbers, exactly, okay? Because they correspond to each other, man. Come on, man. The E field in the photon determines the vertical jiggling in the polarizer in its E field. And then that E field in the polarizer determines the size of the B field that it produces, right? And that, if you're diagonal going in there, right, your E field, that means you're going to have some torque. There's going to be torque, right? And your B field, this way, yeah, you're going to induce a current, like I said up here, but just like over here, you're going to induce a B field and E field that's exactly like yours on their photon. So there's no torque, right? Only when you're diagonal can you be torqued, because E fields and the B fields are in different planes, so you're going to get torque. This is insane. And the amount of torque you get is what? Based on this oscillation. Based on this oscillation. It's not magic, okay? The E field on the polarizer cannot go diagonal. It can either go up and down, or it can go this way. That's it. If this has a little E field, the B field is oscillating back and forth. This guy he's almost 90 degrees with his E field. But, so see, they can't transfer their energy into the horizontal because they need too much. So they transfer it into the vertical, but it depends on how much vertical, power they have, or force. Like this one right here, the more it's vertical, the more it can translate, the more it can translate its force, or is, induced whatever jiggle into the polarizer. This guy, he all of his energy and force or whatever is in the horizontal. It's barely going to do anything. So look at the little jiggle up there. So he got a little, that determines how big your E field and B field is. But now we got another thing that oscillates back and forth. This B field here, right? If it's over, because it's not a line. It's that dot going back and forth that you see, that red dot. When it's here, this is really close. It's the closest one. If he's lucky enough and rolls the dice and he gets this position, he can make it through the filter. That's why even at 89 degrees, you can still got a chance. You can roll the dice, right? This people over here, if these were all polarized almost vertically, that means he's got a big B field. That means most of them are getting it in no matter what position his B field is oscillating in. But even at 1 degree, right, There's a spot over here that's the very end over here. Not the rest of this gets in, but if it's the B field is way down here, you don't get in. That's why you have a